We're going to finish up this section on 3.3. Here we talk about finding an equation of a line when we're only given information about two different points. We're told in the step-by-step guide here that we can start when we're given this information of just simply two different points to identify the slope. Recall that the slope formula given here is a difference in the y components over the difference in the x components. This ratio is often referred to as the rise over run of our given line. If we know the relationship defined by the slope about how one variable changes with respect to the other, we can use the two data points and the slope to then make our equation. We'll select one of the points that's given and plug it into the point-slope formula. The point-slope formula is a rearrangement, if you'll recall, of this slope value. If we remove the subscript for y2 and x2 and rearrange, you can imagine how this could be created. Once we have our equation, we can often be asked to either put it into, as it shows here, the slope-intercept form, or perhaps the standard form. Here's an example asking me to find an equation of a line that contains the 2 points. Write the equation in slope-intercept form. As I come across these, I'll start by labeling the given points. So these are my x1, y1, and x2, y2 values. It may be helpful to then calculate the slope by recalling the formula, especially if you are having difficulty retaining this information. As you come across these problems, practice rewriting the formula before you make your substitution. This will help with recall. So notice that my formula here calls for subtraction. When I enter the numerator values, -2 minus -1, it creates this double negative. Similarly, we can see in the denominator, when we make our substitutions, we get 2 minus -3. So be cautious of this while making your substitutions. In the numerator, I get -2 plus 1, which is -1. In the denominator, we get 2 plus 3, which is 5. So our slope for these two data points, or rather the connection between the variables x and y, is -1/5. What does this mean? It tells me that for every 5 units x might increase, we should expect y to decrease by 1 unit. We can also set this the other way around. If x decreases by 5, we would expect y to increase by 1. So now that we have the slope, we can use our point-slope formula. Which of these points should I use? Well, it is up to me, but as it's labeled here, I'll use the x1, y1 values. Recall the formula is y minus y1 is equal to the slope times x minus x1. So again, I don't really have to use the x1, y1. I could also use this second point. As long as we're consistent, we should come up with the same formula. As we make our substitutions here, I get y minus -2. Again, a double negative shows up in this case. The slope that we just found, being -1/5, gets plugged in, and we have x minus x1, which is again a double negative. So let's clean this up a bit. I could simplify the left side of the equation by removing the double negative, so we get y plus 2. On the other side, I could also simplify a bit before we do our distribution here by saying the double negative inside the parentheses becomes x plus 3. Once we do our distribution here, we'll end up with y plus 2 is equal to -1/5 x minus 3/5. The last step to get into our slope-intercept form is to remove the constant here from the left side of the equation. Those will cancel out, leaving me with the expression y is equal to -1/5 x. And then I've got to do this computation. Really, this is something like -2 3/5. This is a mixed number format, which is really uncommon to see written into an equation and makes algebra difficult to perform. And so we might prefer, instead of -2 3/5, that we reorder this using some process where we convert it into an improper fraction. So we could multiply the denominator value 5 times 2 to get 10, add the numerator 3 to get 13/5 as an equivalent. So there is my equivalent expression in the form asked of us, the slope-intercept format. In the next example, we'll do the same thing. In this case, I want to show not just the slope-intercept form, but as well the standard form. So the standard form is where we have ax plus by is equal to c. We'll go through a similar process here. We'll start by labeling our points. This is my x1, y1 values and x2, y2. Calculating the slope, again, is the difference in the y values over the differences in the x values. Our substitution in this case gives us 4 minus 5 in the numerator over negative 2 minus a negative 3 in the denominator. Looking at the calculations here, 4 minus 5 gives me negative 1. Negative 2 plus 3 should give me positive 1. So our slope can be reduced to just simply negative 1. By substitution, again, to our point-slope formula, again given by the equation you see here, we can replace our values and come up with the expression y minus 4 equals to negative 1 times x minus a negative 2. Notice that I chose to use the second point in this example. While we go through the simplification process here, you'll note that I get on the right-hand side by distribution something like negative 1x minus 2. And adding our constants to the same side here, plus 4 on each side, gives me my solution here for the equation. It should be y is equal to negative 1x plus positive 2. So this isn't quite in the standard form that we suggested we would ask for in this case. The last step to get it into the standard form would be to add x to each side. What that gives me here for my answer in the standard form is 1x plus 1i, 1y is equal to positive 2. So either format could be given or asked for in a case like this. One last example. Here we're asked to find the equation of a line containing the 2 points that you see here, 5, 1, 5, negative 4. What may stand out to you here is that we have a duplicate of our x component. Imagining where these particular values would live in the coordinate plane can help visualize what kind of equation we're trying to create. If my value of 5 on the x-axis is here, I may have a 1 here and a negative 4 here, indicating my 2 points are above and below this x-axis. This generates a vertical line, which has a particular format for the equation. Vertical lines always come in the form x equals to some constant. And you can guess the constant that we're looking for is the repeated 5 that you see in the 2 points given. What is the slope of a vertical line? Well, it's undefined. So we can't use our point slope formula here if the calculation for these 2 points gives us a number where we try to divide by 0. If you go through the motions of trying to calculate using this slope formula, again, the difference in the y values over the difference in the x values will result in this division by 0. So while the numerator could be computed, the denominator gives me division by 0, which causes this undefined nature. So our calculation for the slope is a bit unnecessary, so long as we can recognize the formula for a vertical line is always in the form x equals some constant, where the constant is given by where it crosses the x-axis. This chart sums up important information about these types of problems. When I'm asked to write an equation of a line, you can see that if I'm simply given information about the slope and where it crosses the y-intercept, I can generate the m and b values very easily. If I'm not given the y-intercept but an arbitrary point, I'll need an additional formula here, which is shown as the point slope formula. So quite literally, it's in the name. Slope and point are given. I'm going to use the point-slope formula. As I mentioned before, this particular formula is actually a reorganization of the values that we found using the original slope formula. So it is helpful to understand that connection so that you realize you're not memorizing two separate things. In this case, they're the same. And the last version of this is where I only give you 2 points of information, 2 data points, and ask you to generate a line with that information. The last thing we'll discuss here is finding an equation of a line for either parallel or perpendicular lines. Let's discuss what we mean, or rather the definition of what makes two lines parallel. There's a symbol often used that looks like this to demonstrate that two lines are parallel. And the visual here is just two straight lines that themselves are parallel to one another. The definition we use for parallel is that lines are parallel. For instance, line 1 is parallel to line 2 if the slope of line 1 is equal to the slope of line 2. So this definition is one that we'll need to be able to recall in order to answer the following questions. So here they give me a how-to for this process of finding an equation of a line parallel to some line that's given to me. We'll start by finding the slope of the given line. If we know the slope of the line is supposed to be parallel to a line I'm trying to create, that must mean the slopes are the same. We can also be given a point, and in conjunction with the information about the slope from the first line, we can then create a formula using our point-slope form. This can then be rearranged into the slope-intercept format or the standard form. So let's take a look at an example. Here we're asked to generate an equation that is parallel to the line that's given and passes through a specific point. We know that parallel lines have the same slope. This is, again, a key understanding to answering this question. So the line that's given here, y equals 2x minus 3, again, has a slope of positive 2. Visually speaking, I can kind of guesstimate where this other line would be. I know what parallel lines look like, and so it's likely to look something akin to what we see here. But I need the exact formula for this line. So what we've discovered, again, is that the first line must also have the same slope as the second, which means this is going to have a slope of positive 2. In conjunction with the point that's given to us, I can then use the point-slope formula. So again, the point-slope formula is given by y minus y1 equal to the slope times x minus x1. If my given slope in this case is for the second line, and my given point is negative 2, 1, the formula looks something like this. We might be asked, as I said, to rearrange this into either the standard form or the slope-intercept form. To finish the problem here real quick, we can, in this case by distribution, get something like 2x plus 4 on the right-hand side. And by adding 1 to each side of the equation, we get y equals 2x plus 5 for our solution. So this is line 2. Again, the slope is going to be equivalent to the first line stated here because these lines are meant to be parallel to one another. It also passes through the given point that we were told here. Notice that my drawing is fairly close. If it crosses the y-axis at this positive 5 point, our hand drawing is not too far off. So here you can see that, again, the slope is given as 2 over 1, in terms of the rise and run, it also passes through the specific point that was mentioned. Here's another example. We're asked in this case to find an equation of a line that's parallel to the given one that you see here. So again, we'll call this line 1. The given point will be my x1, y1 values, and these are meant to go through line 2. So if our particular equation is given as being parallel to the one presented here, we must know then that the slope is the same. Our slope of this first line is given by the coefficient on the x term, so 1/2, which means our second line is also going to have a slope of 1/2. This is based again on this definition of what it means for two lines to be parallel to one another. With that, we can now use our point slope formula just as before. So y minus y1 is equal to the slope times x minus x1. By substitution, can be replaced with the given values here for our y1, our value for m, and our value for x1. Now let's do our distribution and simplify. So 1/2 times x and 1/2 times 6 gives me these values. We move our constants to the same side, and we get a solution here for our slope-intercept form of y equals 1/2 x plus 1. So if we like, again, we can demonstrate how this could be converted not into just the slope-intercept form, but also the standard form. So what does the standard form require of us? Just as a reminder, the standard form requires that we have the form ax plus by is equal to c, where the values of our coefficients, a, b, and the constant c, are whole number values. They can't be fractions. So again, our given formula here can be rearranged easily enough. We move our variable x to the left side of the equation by subtraction here. That leaves me then with negative 1/2 x plus y is equal to 1. To eliminate the fraction, we clear it using the LCD, positive 2 in this case. So when I multiply this entire equation on both sides by that value, I get my standard form, which is now negative x plus 2y equals 2. Now let's talk about the other variety of this type of problem where I could be asked about finding an equation of a line that's perpendicular to a given line. Again, the symbol for perpendicularity is this upside down T looking symbol. Our definition is given in this way. We say that line 1 is perpendicular to line 2 if their slopes are negative reciprocals of one another. We can state this in two different ways. Here we show that the product of our two slopes should be equal to negative 1. An alternative way to state this is, as I mentioned, the slope of one line should be the negative reciprocal of the other. We can use either of these definitions. So long as we can recall and utilize them, it shouldn't matter which one you prefer. So let's take a look at how this can be done as well. With a similar setup as before, we'll use our information about the line given to us to identify the slope of the line that we're trying to create. Once we have our given slope and the identified point, we can use the point slope formula again to generate our equation. Here's the same formula and placement of that given point from before. Now we want to graph a line that is perpendicular to the given point and the given line. Perpendicularity in this case would look something like this, where I have a line coming straight and making a nice right angle here where it meets the other line. It should continue indefinitely in either direction, but we need to know the formula and not just a good guess as to what it might look like. So if this, again, is our first line, we've identified, as we did before, that the line of what we're trying to create can be identified using a process of working towards this point slope formula. So if I know the given line here has a slope of 2, my second line is going to be the negative reciprocal. So what should this value be? Again, if line 1 is going to be perpendicular to line 2, then the product of their slopes should be equal to -1. If I replace my equation with the given value for m1, we can see a formula for how to solve for this missing piece of the puzzle. So when I resolve this, I find that m2 should be -1/2. So algebraically, we would just divide each side by the coefficient here, and we get m2 should equal to -1/2, the negative reciprocal of our first line's slope. So given that information, now we can take to our point slope formula. Given here, y minus y1 equal to m times x minus x1. Our x1 and y1 points are given here. So our substitution looks like this. We get y minus 1 is equal to -1/2 times x minus a -2. So I'll write this more simply as x plus 2. By distribution, we get -1/2 x minus 1. And lastly, we'll add 1 to each side to get our equation in the slope-intercept form. Y equals -1/2 x plus 0. Now, normally I wouldn't write the plus 0, but it brings about the point that our intercept for this line that we're trying to create should cross here at the origin. So again, my visual hand-drawn graphic is close, but not accurate enough to give me the full picture. So here's what our equation should look like. And again, you can identify that we have a slope of -1/2 by looking at the fall and run in this case. So let's look at the given example here as our last example for this section. I want to look at this one in particular because there's lots of parts and pieces to a problem like this that can make it difficult to discern. The first of which is identifying the slope. In this example, I'm given, for my first line, a standard form equation. So line 1 here has some slope that I need to know in order to be able to find a line that's perpendicular to it, using the definition of what makes two lines perpendicular. All right, in the standard form, we said previously that if I have something in this form, ax plus by is equal to c, the slope is given by -a/b. So I can use that in this case to identify my slope. If my given equation has values for a, b, and c listed by their coefficients as 1x, -2y, and equal to 5, that means my slope here is actually going to be -1/2, or as we reduce it here, 1/2. So the given slope for my first line takes a little bit more effort to identify. I can't just look at the equation to get it. So if this is supposed to be perpendicular to my second line, what's the negative reciprocal of this value? So reciprocal usually means we exchange the numerator denominator. So instead of 1/2, we can use 2/1. The negative reciprocal would mean adding a negative sign. So -2/1. We could also simplify this as just -2 for the slope. Now I know a point and I know the given slope of my second line that I want to create. Now we can use our point slope formula to identify the equation. By substitution, I get y minus 2 is equal to negative 2 times x minus a negative 2. So let's simplify. We get on our right-hand side, before distribution, x plus 2 like this. Then we can get negative 2x minus 4. And lastly, we'll, by adding 2 to each side of the equation, get our final solution, which is y equals negative 2x minus 2. So this equation is perpendicular to the one that is given, and we're showing it in the slope-intercept form. We could also write it in the standard form by moving our constants, our variable term, negative 2x to the other side. So this would be another equivalent answer for this question. So again, understanding the definition of what makes two lines parallel or perpendicular allows me to find the slope. The slope and the given point here then allow me to use the point slope formula. So practice some of these for yourself. Hopefully we'll see you in the next video.